Video I will do some revision with you about transition metals. I've selected a few questions. This is mainly for my students at school. There are some AQA questions on transition metals, and the key focus here will be some of the questions that come up regularly on the exam. So we'll start with transition metal chemistry, and the first thing I want to focus on is electronic configuration. So the question says that reduce the number of unpaired electrons in copper 2+. So my advice, number one, is do the electronic configuration of copper. And if I just do the last part of it, it will be 4s1 3d10. Now please remember that from your year 12 stuff. When it's copper 2+, electron goes from the 4s first and then from the 3d. How many unpaired? So there's 9 electrons. 1 2 3 4 5 6 7 8 9. 1 unpaired. How does water act as a ligand? So this is just a definition of a ligand. All you need to say that the lone pair of electron on oxygen in water ligand is donated or shared with copper to form a coordinate bond. State what is observed. You should have a sheet of AQA. It's something that AQA released where you've got to learn your reactions. So here the key things I want you to understand is copper 2+ and Fe2+ complex ions. When they both react with sodium carbonate, you get a precipitate and no gas. So what you actually get is you get a blue-green precipitate of copper carbonate, and the equation, this is for a 2+ ion, will be carbonate, which forms copper carbonate and 6 waters. The same will happen with the Fe2+. However, with 3+ ions, aluminium, Fe, or any 3+, vanadium, chromium, the reaction will be slightly different. Because the 3+ ion is a stronger acid than a 2+ ion because it is more polarizing, it has greater charge, smaller size, it can polarize the OH bond, which weakens the bond and releases H+. You will need 2 Fe3+ plus 3 carbonates, and this time you will get a precipitate which will be, as drawn, 2 of those and 3 carbon dioxides and 3 waters. This reaction is one of the most popular reaction that comes up. So that's key. Now, 6 markers. This is a 6 marker that you see in front of you. You've got blue complex and a yellow complex. The blue complex is octahedral with a coordination number of 6, and the yellow one is tetrahedral with a coordination number of 4. As a rule, when AQA asks for 6 marker questions, you're looking at 8 or 9 points. So the best way to tackle a 6 marker of this nature is look at each bullet point. And let's go bullet point at a time. The shape of each complex and why these shapes are different. So number one, all complexes with coordination number of 6 is octahedral. All with 4, as you know, is tetrahedral, except cisplatin, which is square planar. That's now I would draw the complexes, and the reason why CuCl4 2- is tetrahedral is because the chloride ligand is larger than the water ligand, so only 4 Cl- can fit around copper 2+. Now next, how does color arise? As you know, this question appears a lot. So the best way to answer this is, here's your d orbital or d subshell. This will split, and the cause of the splitting could be the ligand, could be the oxidation number of the metal, could be the metal itself, and could be the coordination number. All of these can affect color. But the three main things you're looking at that will cause the d orbital to split: ligand, oxidation number, or the type of metal. So the d orbital will split into, some electrons go into excited state, some ground state, resulting in a difference in energy, which is energy absorbed, which is proportional to the frequency of light absorbed in visible part of spectrum, and you will observe the complementary color. You don't have to say that, you could just say then the light that is reflected is the color that is absorbed. So what are the 3 points here? There are 3 points here: the splitting of d orbital, also known as d-d transition, the difference in energy between the two energy levels. That change in energy, or delta E, is proportional to frequency of light absorbed in the visible part of the spectrum. And the color we see is the color that is either the complementary color of what's absorbed, or you could say the color that is transmitted. Then the question says, why is one of those yellow and the other one is blue? So yellow and blue. Blue is a high frequency end, yellow is low frequency end. So what we will say here is different ligand. So different ligand causes a different, you could say, splitting of d orbital with different energy gap. So you could say that, if that makes sense to that. And then that energy gap is proportional to frequency of light. And then you will say is that yellow is lower frequency, so one of them is yellow because yellow light is transmitted or reflected, and blue is higher frequency and blue light is transmitted or reflected. And that is a 6-marker question there. Now this question is from 2025, and then you will get a question of this nature: excess water followed by excess concentrated ammonia is added to a solution of copper chlorides. What is your observation? You must say deep blue solution formed. You must learn these reactions. And the equation CuCl4 2- reacts with 4 ammonia because copper doesn't undergo full ligand exchange, and that gives you water. With water, and the complex formed is that plus 4 chloride ions. Okay, now here's a question I want to focus on, because a lot of students always complain about calculations. So what I'm going to do here is the following. First of all, you've got to learn the equation between dichromate and manganate. I'm not going to do the equation, I'm going to do this molar ratio here. Now what do we know? The average titer here is titer 1 and titer 3, 28.55, because they are concordant. Next, the question is calculate the MR of the whole complex. So you're working out the MR of the whole complex. What do we know? So, number one, we can work out the moles of manganate ions because we know its concentration, which is 0.02, and we know the average titer, and that gives me the moles of manganate, which is 5.71 times 10 to the minus 4. The rule always. So number one, moles, followed by molar ratio. Then is the solution in 250. So now the moles of C2042 minus. Molar ratio is 2 to 5, which means 5.71 times 10 to the minus 4 times 5 over 2. Now, if we look at the solution, it was made up to 250. 25 of the complex of M is titrated. So at this stage, I'm also going to multiply by 10. And up to here, most students will have got this answer of 1.4275 times 10 to the minus 2. Now comes a really important thing. So the complex is M2 Cu C2 O42 H2O there. It contains 2 C2O42 minus molecules. So one of the key things that will get missed out now is to determine the moles of the complex now, because we are working out the MR of the complex, and this is where we have to divide by 2. So we've got to divide 1.4275 times 10 to the minus 2 by 2. And the reason is because we divide by 2 to get the moles of the complex, because 1 mole of complex contains 2 moles of ethane diovate. And that's the bit you've got to sort out in order to get the marks. That then gives us 7.1375 times 10 to the minus 3 moles of the complex. So that's moles of complex. And then to work out MR, you take your mass 2.52, you divide by the moles here, and you will get an answer of 353. And then M2 equals 353 minus the MR of the whole of this complex I'm highlighting for you. And that comes to 275.7, 277.5, which gives you 77.5. So M equals 77.5 over 2 because it's M2. which comes to around 38.8, which is potassium. Potassium ion or potassium metal. Potassium ion, sorry, not metal. So that, again, let me go through it. Moles of manganate, molar ratio 10 to 50, and then comes the hardest part, because 1 mole of complex contains 2 moles of ethane diovate, and then the rest hopefully is straightforward. Draw 2 structures. Now you've got to be able to draw structures properly. When you have an octahedral complex, my advice is to draw the skeleton, and because we are dealing with stereoisomers, we must always start with 3D arrangement. I'm going to put my waters here, and I'm going to put my diovate ion here, square bracket, and then the overall charge. You could do the mirror image of this, and that would be correct. Alternatively, you could swap the OH2 and you could move it here, and that would give you cis or Z. The one we drew before was E or trans. So that is a question which hopefully will help you to understand how to do a calculation. And if you see a repetition, so that question we've just done, this shape here, is from a 2025 paper. This one's from 2024, and it's asking you for that. Again, same procedure, and you draw your oxalate. The only difference is this time you've got 3 oxalates. Just pause the video, slow it down to watch what's going on, and don't forget the overall charge 3 minus. Okay, now I want to focus on this 6 marker in front of you. All right, chelate effect, again, learn the definition. Basically, the monodentate ligand is replaced by a bidentate or multidentate ligand, results in a much stable complex formed because there is positive entropy change or entropy increases on the right hand side, and the delta H is negligible, which means delta H, G will be negative, so the reaction is very much feasible. Again, let's look at the 6 marker. Outline how Fe2 plus catalyzes the reaction between these two. Now, firstly, it's again a reaction you've got to know. You've got to memorize this reaction. So I'm going to write this reaction here. Reacts with 2I minus, forms I2 plus 2SO4, 2 minus. So this is the bit you've got to memorize, otherwise you are not going to be able to answer this question. Sketch a graph of how concentration so changes over time of persulfate. Look, I'm going to show you why it's so important to draw the axis properly. Okay, so we're doing the first bullet point first. Concentration of S2O8 2 minus in mole per dm cubed, time, second, minute, and standard graph. Okay, make it nice and smooth. This is not very smooth, but okay, it doesn't touch. Make sure it doesn't touch the x-axis. Nice 2 marks here. Changes over time. You don't even need to say anything. So there's your level 1. 2 marks. Explain how Fe2 plus catalyzes a reaction. Please remember, 6 markers in AQA need to be perfect. They need a lot of details. So number 1, Fe2 plus acts as a catalyst because it has variable oxidation states. Number 2, the S2O82 minus ion and I minus ion both are negative and repel. So the catalyst, so they have high activation energy. The catalyst will provide an alternate pathway with lower activation energy. Now we can do both of these two together. Well, the overall equation we've done there anyway. Now how does it catalyze? In the first place, Fe2 plus attracts or reacts with S2O82 minus because a positive species is attracted to a negative species. So Fe2 plus reacts with S2O82 minus to give you Fe3 plus and SO4 2 minus, and note oxidation of Fe2 plus and reduction of sulfur. Second step, 2 Fe3 plus reacts with the iodide now, produces iodine, and 2 Fe2 plus, a catalyst used in step 1, regenerated in step 2. There you have a full 6 marker question for you to really look at, slow the video down and just follow the steps through. But you must remember these reactions, otherwise you're gonna struggle. Okay, then the question says a student adds ammonia, give the formula of the precipitate forms. Well, the precipitate will be that. So let's look at the repetition. Student adds Fe2 plus to carbonate, and I've already actually answered this question for you further up here when we were looking at copper, and I did say to you it comes up a lot here. Just replace copper with iron. So you can see this repetition, and again these questions are from the last 3 years or 4 years of papers. So you can see that repetition. You've got to memorize it. Fe2 plus changes to yellow brown after contact in air. That means it's been oxidized. So it's Fe3 plus, and that equation we have already looked at. This one, and that's on the top again, so you can go back to the video of that. Do these as ionic equations, they're much easier for that. Lastly, there are 2 more questions I want to look at. Let's look at this question. It says 4D. D, it doesn't matter the number. Again, I want to highlight for you how to tackle these questions. 0.15 gram of ammonium vanadate. The vanadate is converted. The famous reaction of vanadium with zinc. The filtrate containing V2 plus is titrated with manganate. So now look again, manganate, and 29.43 of manganate. What am I going to do straight away? I'm going to work out moles of manganate, and I haven't even read the question yet. 43 over 1,000. The question above 0.02 we had 28.55. That gives me 5.89 times 10 to the minus 4 moles. Then The ionic equation for the reaction, 3 manganate to 5. So now the molar ratio is 3 to 5. So number 2 moles of V2 plus is 5.89 times 10 to the minus 4 times 5 over 3. Again, is the solution of 250? There's no mention of 250, so we don't need to multiply by 10 here. We just get 9.81 times 10 to the minus 4 moles. Calculate the percentage purity. So now mass equals moles times MR. MR of ammonium vanadate is 116.9. So 9.81 times 10 to the minus 4 times 116.9 comes to 0.1147 grams. And then your percentage purity 0.151. Just divide times 100 and you get an answer of around, let me just double check, 0.1147 divided by 0.151, 75.96, so 76.0, perfectly fine. There's your answer. Okay, last one. Some complexes containing transition metals are colored. So now if you go back to this question, okay, so I'm just going back to the first, right at the top we did a 6 marker here. We talked about shape, color, and why some are colored. Look at the repetition of the question. The question is repeating, and this is repeating over a period of 4 to 5 years. Why are they colored? Okay, so we need about 3 points here. List the factors that affect color. That we've already talked about, haven't we? The metal, the oxidation state. Please don't abbreviate. The ligand, the type of ligand, and the coordination number or shape. So that gets you 2 marks. And describe our calorimetry. And now let's tackle these 2 bullet points together. Why are they colored? Again, d orbital splits, number 1. By the way, the splitting is always 2 to 3. So there's your excited state, there's your ground state. So just say this, the d orbital splits. That's actually 1 mark. Some electrons move to higher energy level, some to lower energy level. So this movement of electrons resulting in a difference in energy between the 2 energy levels. Resulting in a difference in energy between the 2 energy levels. That energy is absorbed in the visible part of the electromagnetic spectrum, visible light part, resulting in, or don't say result, say that energy change is proportional to frequency of light that is absorbed in the visible part, and the complementary color is observed, or you can say the color of light that is reflected or transmitted is the color that is seen, that is observed. So again, the splitting of the d orbital, the movement of electrons to 2 different energy levels, higher and ground state, difference in energy delta E between the 2 energy levels, which is proportional to the energy, to the frequency of light absorbed in the visible part of the spectrum, and the color that you observe is the one that's reflected, or the complementary color. And describe how colorimetry. I'll say this to you, even if this doesn't come up a 6 marker, you will get questions on how color is observed, why they are colored, and colorimetry. With colorimetry, number one, take about 5 to 10 solutions, okay, of different concentrations. The best way is to do serial dilution. Take a solution like 0.1 molar and dilute it 10 times. Simply, how do you dilute? 1 cubic centimeters of solution, 9 of distilled water, and so on. Then measure the absorbance of each solution of concentration. Plot a graph of absorbance against concentration. You get your calibration curve, and then measure the absorbance of the unknown, and then measure its concentration. And that